Eventually, this is actually the key to study properties. But at this point, after this module, it might be a bit strange. Why am I teaching all this? In the connection to properties, any kind of property, it might be sort of difficult to understand at this stage. But please bear with me. Again, this might be a bit confusing, but hopefully we'll all be in the same page. Okay. So it will be a quick introduction. Then we will see the Schrodinger equation, the two sort of main Schrodinger equations, time independent and time dependent, the free electron model, electron in a potential well, electron in a periodic field of crystal. Then we'll jump into energy bands and Fermi level. Hopefully we'll get until energy bands at least in this class. So, quick intro. We sort of know certain properties or a lot of properties of different materials, but we've always learned these properties in terms of macro levels, right? And we actually learned the result of them, but not really how they develop, right? And that's the key of this class and of this module. It's trying to dip into what's happening inside the material. And for that, we really need to know what's happening at the atomic level, and that means what's happening with electrons or phonons once we get to them. So really understanding how electrons behave is quite important. Electron theory provides important fundamentals for any technology that we know that's considered basically the basis of modern civilization. Everything you know now, absolutely everything, TVs, computers, everything, is related to electron theory. So, electron theory is capable of explaining optical, magnetic, thermal, electronic, electrical, every single property of a material. And so let's sort of draw a timeline on how these things were developing until we know now and what we obviously we want to study now, right? So around the 19th century, everything by then was explained through experimental observation, right? Absolutely everything. For example, Maxwell equation, Newton's law, if you remember the apple falling from the tree, okay? That everything was explained with experimental observation. And obviously, the laws that were sort of regulating that behavior were empirically derived. And so basically, that theory that's called the Continuum Theory was sort of explaining and relating macroscopic quantities to experimental data, right? And that was how everything was sort of related at that point. There were no assumptions about the structure of matter and about certain equations. It was all just relating macroscopic quantities with experimental data. That was continuum theory. But then, sort of at the beginning of the 20th century, there was sort of a refinement in understanding the properties of materials. And the classical electron theory was born. At that point, this theory was only saying that free electrons in metals drift as a response to an external stimulus, right? And that usually means an external force. And these electrons interact with lattice atoms. And so it was quite simple, sort of trying to understand how electrons work. And again, everything what was saying is just electrons, free electrons drift as a response to an external stimulus and interact with other atoms. And that was it. But then, at the beginning of the 20th century, let's say around, actually probably mid-20th century, the main theory was developed, the quantum theory. This approach was able to explain all the important experimental observations which were not, at that point, were not able to be explained by classical means. That means by the classical electron theory, right? And so things became a lot more difficult because people realized that Newtonian mechanics became completely inaccurate when we were talking about atomistic dimensions. So everything what was explaining at what was being explained at a macro level with laws like Maxwell equations, Newton's law, so all these things that were explained at a macro level, when we were trying to use, when they were trying to use those laws to explain what was happening with atomistic dimensions, everything became inaccurate. And that's why quantum theory is important, because it's able to explain what's happening with atomistic dimensions. It's able to explain what's really the key that's driving all this behavior of materials. The big problem of this theory, though, is that it lacks visualization for us, and this is why this topic is so hard, because it's so difficult for us to visualize the phenomena that these equations or that this theory is describing, because it's obviously at a level that it's quite small, that it's really difficult for us to visualize what's happening. And that's the big problem of quantum theory, and that's why it's so hard. That's why a lot of physicists and mathematicians and material scientists struggle, because it's sort of difficult to, when you're explaining Newtonian mechanics and all the other laws that explain how materials behave at a macro level, it's sort of easy for us to visualize and sort of understand. But at that level, at the atomistic level, it becomes impossible. But we'll sort of try to understand that. Okay. And before I jump into the actual content, I wanna mention these few equations because they will be quite important soon. We all know Newton's law, super easy. We all know the kinetic energy equation. Okay, I think we all know that. Momentum, mass times velocity, we all know that. Momentum of an electron, right? Momentum P is equal to the mass of the electron times the velocity of the electron. And that's why if we combine the two previous equations, this equation will be quite important. This equation will be quite relevant. The energy of an electron is equal to the momentum square divided by 2 times the mass of the electron. This is going to be extremely important. The speed of light, that relates the frequency of the light wave to the wavelength. Okay. The velocity of the wave, the velocity relates the frequency of the light wave as well to the wavelength. So basically the speed of light sort of becomes the same as the velocity of a wave. because light is a wave. Angular frequency, this will also be important. 2 pi times the frequency of the light wave. And Einstein's mass energy equivalence, we all know energy, mc squared, right? Okay, so just keep this in mind. We will all, at the end, we will end up using all of them, but there will be a couple of them that will become extremely important soon. Okay. What this equation is. Have you seen this equation before, guys? You should have. Well, I'm not sure. I'm not sure about your differential equations course, but this is one of the most famous equations you can all learn. And it's usually taught when you're learning about differential equations. I don't know if you were taught this equation. Have you seen it before?
Yes, in advanced mathematics.
Yeah, which equation is this
We
one?
learn how to solve it. It's the Schrodinger equation.
Okay, cool. Time dependent or time independent?
Hmm. I, I guess time time dependent.
Well, it's this one is time independent. You don't see the t there, right? There's no t in that equation. There's no time here.
Mm.
Yeah. So this is the most famous equation, the Schrodinger equation. And this is actually the basis for all what we're gonna learn in this module. This is the basis. Okay. If you learn how to solve it, amazing, because we will need to solve it. And we're not gonna do that in this class. We'll do that in the tutorial. We'll see how to solve it in certain different situations. But here we're gonna relate this to what matters. Okay. So as I say here, I'm not gonna derive also the Schrodinger equation. I'm not sure if you did it. You might have done it in your differential equations course. I'm not gonna teach you how to derive it. That's more for mathematicians and physicists who really want to understand quantum mechanics and like they really need to understand it. Um, we're really not interested in that. We're more engineers, okay? So we're not gonna derive the equation, but we're gonna solve it, and we're gonna see how this equation relates to what we need to learn. So for the purposes of this class, we're gonna consider the Schrodinger equation as a fundamental equation, such as Newton equations, for example. So we're gonna take it as granted. Okay, we're not gonna derive this equation again because that's not really the purpose of this class. Okay, so we're gonna start with the previous equation I showed, the time-independent Schrodinger equation. When are we gonna use this equation? When we want to learn about properties of atomic systems in stationary conditions. So that means when the system of atoms is really stationary. And you're going to say, well, but how is it possible? How is it that the system, an atomic system, can be stationary? Well, it just means that you're taking a system at a time that, it's, let's say, time zero, and you're just considering the system at that moment, and that's it. I mean, you don't care about time. And to be honest, in quantum mechanics, and this is why it's difficult to visualize, this is actually the case for most applications we'll study in this course. So that means electric properties, thermal properties, all of them have been developed through this condition. that the system is in stationary conditions. So that means the property of the surroundings of the electron doesn't change with time. And it's actually the case, again, for most properties we're going to study. So if we sort of relate what the meaning of this equation is in terms of atoms or electrons, the time-independent Schrodinger equation is basically an equation of a vibration. It's basically describing a vibration. That's it. Obviously, vibration of atoms, which means vibration of electrons, right? And the energy, because it's time-independent, I'm gonna go just a bit ahead. The energy, it's time-independent, and therefore only depends on the location, but not on time. Okay, so this is the equation again, right? Can anyone explain? You guys said you've seen this equation before, and I'm glad you did it. Can anyone explain term by term what basically what's each term in this equation? If not, I'm gonna choose who's gonna explain. Okay, let's go with Julio. Julio, are you there?
Yes.
Okay. Do you remember what each term means in this equation? What's this? What's the first term?
I don't remember, Mr. Sorry.
Okay, Julio.
Yes.
Okay, guys, who remembers this?
The only thing I remember about the equation is that E means kinetic energy and V means potential energy, if I'm not wrong.
Okay, kinetic energy, potential energy, that's perfect. How about M? How about this symbol?
I'm not really sure if N means something mass, but honestly, I don't
Okay,
really
thanks, Nati. Who remembers, guys,
The
what
moment
this
square. This
H is moment?
mm,
Well, sort of, it's not really an H, right? But let's say H.
It's the Planck constant.
But
A variation of the Planck constant.
abbreviation. What do you mean by abbreviation of the Planck constant?
Variation. I mean,
Oh, variation.
it's not the original. I don't know the quantity, but I think that it was multiplied by an imaginary number and something like that.
Just, okay. It's just the Planck's constant divided by 2 pi, sorry. Okay, it's just the Planck's constant divided by 2 pi, so it is a constant, yes. And m is just the mass. And obviously, the function here is what matters, right? The function here we have, that's really the key. That's called the wave function. Okay? The wave function, if we're considering a 3D case, we'll obviously have to take the differential of the wave function with respect to x, y, and z. But we'll start just with 1D. we'll start considering the one-dimensional case, and therefore we're gonna, let me choose a color. We'll just start using this term, right? Because we'll start with the one-dimensional case. So the differential of the wave function, this is the wave function, the important term. The wave function with respect to x, y, and z. And if we will have time here, it will also be the wave function with respect to time, right? But that's not the case now. So E becomes actually the total energy of the system, and it provides values for all the allowed energies once the potential energy and the wave function are given. Okay, that's why I'm saying here E actually becomes the kinetic energy plus the potential energy. So E actually becomes the total energy of the system. Okay. That's with regarding the time-independent Schrodinger equation. If we jump into the time-dependent, then all what's going to change is just this term, right? That the wave function, it now depends not only on x, y, and z, so that means on the directions the atoms and obviously the electrons are moving, but it also depends on the time, right? And therefore, I mean, if we were to solve this, right, and we eventually will do this problem in the tutorial, this just becomes the wave function, right, times E to the I times the frequency times time, right? So basically, the wave equation now contains the differential or the derivatives of the wave function with respect to space, with respect to the directions, and with respect to time. And then, you know, you can solve all this. And again, I think we'll do this in the tutorial. I'm not gonna, you know, spend the time just deriving this, but this will be the solution of this equation, right? If we solve this, we'll get that solution. So it will be the differential of the wave function times all well, minus this term and minus this other term. Again, here is not really, you know, this is just how you solve this, and again, I think we'll do that in the tutorial. Okay, and then we can rearrange this. Okay, if we rearrange this equation, we will get this, and this is actually the solution of the time-dependent Schrodinger equation. If we were to solve, you know, fully the previous equation, we'll get this. And you can see that the variation of the Planck's constant is there. Obviously, there is an imaginary component, and we have the mass of the electron that hasn't changed. The potential energy is still there, right? And the key part, right? We have a differential of the wave function with respect to a space. So that means with respect to x, y, and z, or only x if we're considering the 1D case, and the differential with respect to time, right? So this is just a quick introduction to the two main types of Schrodinger equation. And we'll use this at some point, but the main one, the one that actually matters for us, is this one. Because this equation is the key to solve and to understand all the properties we're going to study. The time-independent Schrodinger equation. to sort of demonstrate that, let's do this, guys. Let's go to the first and simplest case of the Schrodinger equation, talking about free electrons. What does it mean when I say a free electron? Well, it just means that electrons propagate freely. That means in space that there is no a potential barrier. There is no a potential well. There is no potential energy, basically. So that means electrons propagate freely, no barrier, they can move around entirely free. And for the purposes of simplicity, let's consider only the 1D case, the one-dimensional case. And so we're just going to consider that it's moving in the x direction, right? If we consider that, guys, so remember, this is a simple but very important case. It's the first case, the simplest case, but it's very important to understand what's happening with electrons in certain conditions. And I mean, in certain conditions, I mean specifically in this condition, where there is no barrier, there's just free space, and the electron is just moving. If we consider a 3D case, it's moving all in 3 directions. Let's just consider the one-dimensional case, it's moving in the x direction. So, if we have this equation, guys, how this is gonna change, or how this concept of free space or free electron moving in space, how this is gonna affect this equation. So if I were to change this or adapt this equation, the Schrodinger independent time independent equation, how this is gonna be, or what's the shape this equation is gonna take with this condition, that the electron is free, that the electron is moving with no barriers.
Maybe V equals 0.
Perfect. B, the potential energy is going to be 0, right? And if I'm considering that this term, the differential term, I'm considering only, again, the 1D case, right? That's why I highlighted positive x direction. I'm just considering the 1D case. So that means the differential of the wave function is going to be only with respect to x, okay? That's the one term. Then this doesn't change. 2m divided by the variation of the Planck's constant, the square, that's the same. E, the energy, the total energy doesn't change, but absolutely this is right. The potential energy becomes 0 because there is no potential energy. There is no any barrier. There is no wall restricting the movement of electron, and therefore the potential energy is 0. So it becomes just times the energy times the wave function, that equals 0. Is it clear so far, guys? Are we all in the same page so far?
I got a little confused about the potential energy being 0. Why is it again?
Because the electron is moving freely. It's propagating freely. We'll see later another case when the electrons find barriers. The potential energy is basically related to how the electron is moving. If the electron is moving freely, it can propagate all around with no restrictions. That means there is no barrier for the electron movement. And that means there is no, when the electron is moving freely, when there is no barrier, the potential energy means it's zero, because it means there is a potential free space, as it says here. Sorry, where's my, okay. It's a potential free space. When the electrons propagate freely, they can move all around with no restrictions. It means the space where they are, it's a potential free space. So that means there is no potential energy, sort of restricting or sort of blocking the electron of the movement of electrons. That's why if you actually realize, let me erase all this. If we just focus on this term, that's why you usually subtract the potential energy from the total energy. You subtract the potential energy, because the potential energy is the barrier. So usually what matters to the Schrodinger equation is the rest of energy that the electron has, or well, not the but sort of it's related to the movement of electron. That's why you usually subtract it, because the potential energy is a barrier for the electron movement, because it's sort of blocking, sort of absorbing the rest of the energy that's present in the system. It's sort of absorbing and therefore blocking or restricting the movement of electrons. In this case, if we're considering the case of a free electron, the electron moving all completely around, that means there is no barrier, and therefore this term becomes zero. Is that clear, Fernando?
Yeah, I kind of get it right now.
Okay, how about the rest? Is everyone following, guys? I really need this to be clear for everyone, because this is going to be quite important.
Yeah, it's very good.
Okay. Okay. We'll solve this definitely in the tutorial, but we all know, and I guess you all might remember, if you solve this equation, this basically becomes an equation for an undamped vibration. That means for a vibration that doesn't have any fixed support, right? If you, I don't know how you learn this equation in the solution, but if you relate this for a vibration of any system, this is basically equivalent to a vibration that is undamped. That means that doesn't have any support at the end. It's just the vibration. And therefore, the solution is this one. And again, we'll do this step by step, hopefully in the tutorial, and you will do it, and I'll guide you through it. But that's the solution. A, it's a constant, right? This becomes basically the wave function becomes a constant times the exponential of I times alpha times x. X means the position, right? And alpha is the key. What's the meaning of this symbol alpha? Well, alpha is sort of a constant related to energy, right? It's just the square root of 2 times the mass times the energy divided by the variation of the Planck's constant square. So for the purposes of the class, I can call it just Planck's constant, but remember, it's not really the pure number of the Planck's constant. No, it's divided by 2 pi. Okay, so if we rearrange this and solve for E, for the energy, what are we gonna get? Well, that's quite easy, right? We just rearrange this, solve for the energy, and we get this. And that term is going to be extremely important. So save this equation because we're going to use it a lot. So the total energy.
David, what's the meaning of alpha? Can you repeat it, please?
Alpha is just a constant. I'll give it a name soon. For now, we're just going to consider it's a constant related to energy. I'm going to give it a name soon. Just bear with me. Okay. But for now, let's say it's part of the wave function. Okay. I'm going to give it a name soon because there will be a correlation between certain terms. But for now, let's consider it's just a constant related to energy. Let's say alpha is a constant related to energy. Okay. We'll see in a moment what exactly alpha means. But save this equation because it's going to be quite important. And this is the total energy of a system where I have free electrons, where I have electrons moving with no barrier. So, if you see this, guys, if you just see this equation of energy, because remember, this concept of energy is going to be important for everything else we're going to learn. If you see that equation, and I'm saying basically alpha is just a number, it doesn't really affect something. Would you say that all the values, all possible values of energy are allowed when we're talking about free electrons? Or when you see this equation, do you see any possible restriction of values? Certain values that might not fit into this equation? Or do you think all values of energy will be allowed?
There is no infinite energy, therefore, because mass has to be something bigger than zero.
Yeah. So for you, there is no restriction of values, right?
I mean, and the only restriction will be that mass has to be other than zero, and also it has to be positive.
Yeah, obviously, right? So what I mean is there's no any condition that might block certain values of energy. That's my point. There's not really a condition because obviously if it's zero, well, you cannot divide it by zero, but obviously the mass of an electron is not going to be zero. It's impossible for the mass of an electron to be zero, right? So basically, considering this, do we all agree that the value of energy can be any value? And that means all values of energy are allowed when we're considering free electrons. Do we all agree on that or no?
Even though, I mean, energy, I think energy shouldn't be a negative number since it's inside of a square root, or
Yeah,
it doesn't
obviously
matter.
energy is not going to be a negative number because the Planck's constant is not negative, the mass is not negative, and alpha is definitely not going to be negative. So obviously energy is not going to be negative. But if we consider all positive values, then all the values of energy are allowed. Am I right or am I wrong? Or do you see another restriction? Obviously, energy is not going to be negative. I agree with you, Natalia, and it's just impossible for energy to be negative in this case because the Planck's constant, mass, and alpha are all positive. So, and even though if they will be negative, this is a square, right? The Planck's constant is a square, alpha is a square, so anyways it's going to be positive. The term at the end is going to be positive, and mass, obviously, the mass is not going to be negative. So if we're talking, about positive values of energy, are all energy values allowed?
I will think that it has to be like a constant because the mass of an electron has to be like a fixed number. So I would say it's not like you have an entire range of possible energies, but a little range because the mass varies, but it's a little variation.
Well, mass and Planck's constant are not going to change. Basically, I agree with you, but this number is going to change. This number is going to change. Alpha is going to change. And that will obviously affect energy. That's why I said alpha is sort of a constant, but not really, because it's related to the total energy, right? And alpha is going to change. And I agree with you, mass and Planck's constant, there are fixed numbers. They're not going to change. But that small term that we'll see what it means is going to change.
Maybe I think that alpha is related to the speed of the particle.
Yeah, we'll see that. We'll see that soon, because I want to connect this concept to other things. And I think if we sort of connect them all at the same time, it will be easier to understand. So, okay, so far I have no restrictions of energy, of values of energy, because I have no boundary condition, because I said it's an undamped vibration. That means a vibration that doesn't have any fixed ends. And that means there is no boundary conditions that's restricting that. So I have a free flying electron moving all around. Therefore, all values of energy, and again, all values are going to be positive, all values of the energy are allowed. And that's what we call an energy continuum. You see this little box here? That means what's happening now. I can have all possible values of energy when I'm considering a free electron. That means I get an energy continuum. That means there is no restriction of values of energy that my system can take. There is no restriction. Basically, the system can take any value of energy. And that's why I get all this full block of values of energy, because there is no restriction. And at this point, this statement might seem quite trivial, but when we jump into the next case, that is the bound electron, you'll see why is this so relevant. So at this point, again, you get an energy continuum. That means a full range of values of energy that are possible, that are allowed for the system. Basically, there is no restriction of energy values. So far, so clear, guys?
And there's only one thing I'm thinking about. Once you find the energy, it's not like the electron is going to have another energy. I mean, it's not going to increase, it's not going to decrease. It's a fixed value once you find it, but it could be anywhere in that energy continuum.
Oh yeah, for sure. Yeah, I mean, the initial value, it can be any value, right? And there is no restriction for that value to be. Yeah, and then I mean, the energy, because of the law, it has to be constant energy. The energy doesn't change, it doesn't disappear. Sorry, it doesn't disappear. It just changes, right? But yeah, basically what this means is that you can get any value of energy. That's the point.
Okay.
Yeah, the system can take any value of energy in this range, and this range is really quite big, because there's no restriction, right? As long as it's positive, but obviously energy is going to be positive, it can take any value. Okay, and one thing, guys, remember, this is not going to be easy to visualize. And that's really the hard part of quantum mechanics. As I said at the beginning in the introduction, It's very difficult for us to visualize this. And that's why I sort of want to clarify certain concepts. Okay? Certain laws, as I said, actually not certain, the laws that explain, you know, the behavior at macro level are not going to be the same that explain the behavior at the atomistic level. Okay? And that's why you really need to be focused on these concepts I'm explaining now. Okay. So when I'm talking about energy continuum, okay, I got this, right? I got this equation is equal to, okay, that equation that I said is quite important. But if we go back to, I'm sure, sorry to go back so much. Okay, let me see if I put this equation here or no. So I can relate it to, okay. If we solve, I think I didn't, let me see if oh no, actually I did, yeah, okay. If you remember this equation, sorry, this equation here, keep that equation in mind, okay? Remember that in this case, the total energy is just the kinetic energy because there is no potential energy, right? So it's just the momentum squared divided by 2 times the mass. If we replace that, if we replace E by that momentum, let me see, momentum squared divided by 2 times the mass, right? What's going to happen? If we replace that here, right? What's going to happen? 2 mass with 2 mass, they cancel, right? And I just end up with momentum squared divided by the Planck's constant square. Square root of that, I end up with momentum divided by the Planck's constant. Do you all follow until there?
Yes, mister.
Okay, just system equations. Let me see if I have the other equation here. It seems I missed it. I wish I have it here. Let me see. No, I don't see that equation here. This is gonna be quite relevant as well. I think I forgot to put it there. But then, okay, let me delete this. Well, actually, I'm just gonna use another color. Let's focus on this now. You wanna say, okay, how do you get, because this is obviously something relevant, how do you get from momentum divided by the Planck's constant? How is it that you get 2 pi over lambda, or over the wavelength, right? And how's that equal to K? Well, there is a key equation, okay, that says that the wavelength is equal to the inverse of the wave number, and this is what matters now, the wave number, that's k, okay, the inverse of the wave numbers times 2 pi, and 2 pi is just because of the frequency of a wave. Remember, 2 pi is just the frequency, it's just related to the frequency of a wave, right? So that's why you multiply it. So basically the wavelength is, it's the inverse of the wave number, okay, 1 over k times the frequency, right? Because the wave frequency is usually 2 pi. Okay, so that's gonna be easier, I think, to understand. So let me delete this now. And therefore, the wavelength is equal to 2 pi over the wave number, or over k. So, and there is another equation that is also not here, and I forgot to put it at the beginning. That says that the wave number, the wavelength, sorry, times the momentum. Let me see if I have something that I can relate to the first equation so you understand it better. No, I don't see anything that we could use. Yeah, definitely not. That might help. No, really. Okay, no, I forgot to put it, but okay, I might add it once I upload these slides to Aula Virtual. But there is an equation that basically says that the product of the momentum of a wave times its wavelength, it's equal to the Planck's constant. And that's really the Planck's constant. But if you remember, okay, I'm gonna delete this now. If you remember, what I said is that this symbol here is not equal to the wave, sorry, to the Planck's constant, but this is actually equal to what? What did I say?
2 pi divided to Planck's constant, I think. Or 2 pi times constant. Planck constant.
So you say this. Oops, sorry. Oops, oops, sorry. It's actually okay. This is the key. So that means that the momentum of a wave times the wavelength is equal to, well, you can solve for h here for the Planck's constant, and you will get this variation, right, times 2 pi. Sorry. No, it's actually, this is wrong. I'm sorry. Okay, let me do this again. Okay, that's the equation. So this is the key. Let me just write down these equations again, because this is quite important, and this equation as well. Okay, 2 pi over the wave number. Okay, those two equations are quite important because that can help us sort of solve this symbol that I said before, that's alpha, right? So with this equation, remember that this will be basically this will be 2 pi times h, right? 2 pi, oops, yeah, 2 pi times the sort of variation of the Planck's constant. Okay, therefore, this is, yeah, the Planck's constant divided by 2 pi. And that is, if we solve for h here, for the Planck's constant, we get the variation of the Planck's constant times 2 pi, and that's what we replace here, right? Therefore, I can, if I take this this relation, let me change colors now. If I take this relation, the momentum times the wavelength is equal to the variation of the Planck's constant times 2 pi. If I take the ratio, momentum by Planck's constant is equal to 2 pi divided by the wavelength. So it's just basically from this relation, I come here down and I can take these ratios. But I also know that from this equation here, that 2 pi divided by lambda by the wavelength is equal to the wave number. And therefore, this little alpha that we didn't know what it means, it's actually equivalent to the wave number. And remember, the wave number is just the inverse of the wavelength times 2 pi. And that means just because it's just the frequency of the wave, right? But it's in simple terms, it's just the inverse of the wavelength. So alpha becomes the wave number. I know there's a lot of equations here, but did you guys follow? I think there's sort of simple equations. Did you guys follow? Is it clear?
Yes, mister.
Yes,
So in the very end, it only depends on the wave number, the total energy. That's why we have this continuum energy.
Yes, that's right. That is right. Any other questions, guys, or is it clear for everyone?
So alpha will be the wave number if and only if we are dealing with free flying electrons, right? Just in this case. It might be happening with restrictions as well.
Yeah, and we'll see that. But yeah, alpha might change if we have another case, or might not. We'll see that. I really want to sort of start digging into these concepts, but so far, let's say alpha is the wave number.
Okay.
Any other questions, guys? No.
So with K, we will relate the material to the capacity to conduct energy.
Yes.
So
I mean,
K is a way to identify a certain material. No.
sort of yes, because K will affect the energy, the possible values of energy, and therefore, yeah. I mean, if you sort of want to be very sort of, I guess, detailed, we could say yes, because K will be related to energy, and the values of energy that a system can take will be different from one case to the other. But I wouldn't say probably it's really a way to identify a material, because it's more to the way to identify certain situations, but different materials can behave the same way and I mean, as long as I have free, let's say in this case, as long as I have free electrons, it could be
There is no
any material.
difference between materials.
Yeah, so I wouldn't say it's a difference between materials. It's more a difference between how that material is behaving, and that means I can have a bunch of materials all behaving the same way. So that means all having free electrons in certain conditions, and therefore we all will behave with this. Well, they will all behave this way. So that means they will all be able to take all possible energy values.
Okay.
But definitely we'll see, and we'll go, sort of jumping into that, how, for example, metals, semiconductors, and ice insulators, how they differ, and how this value of energy becomes different from metals to semiconductors. We'll see that difference, and then you could say, okay, this sort of relates to K, but that would be sort of more of like a trying to explore different relations. But yeah, I mean, at the end, it does affect, but I wouldn't say it's a specific. It's a value specific to a material.
So I have a question. So what can I get as a conclusion from this number? I mean, if I have a bunch of different alpha numbers, what can I say about it as a conclusion if I have to let's say analyze them?
Well, so far, the conclusion is not really about alpha or about K. For me, what's more important, it's the conclusion about the values of energy, because that's what's gonna define everything. The values of energy is what's gonna matter when we start digging into the study of the different properties of materials, and the difference between metals and semiconductors. It's all about the energy. K and alpha are just numbers that are contributing to the value of energy, but what matters here is the value of energy,
So
and the values of energy that a system can take.
is it directly related to the energy gap?
Yes. So that's the conclusion I really want to emphasize. And hopefully that's the conclusion you all want to have. K is just the wave number, it's just the inverse of a wavelength of the electron. But that's not really, let's say, the key concept. The key concept here is how that affects my energy. And in this case, the way it is affecting it, it means that the energy can be any value. All values of energy are allowed, as long as it's positive, but all values of energy are allowed. And that's my main conclusion here, that when I have a free electron, the values of energy are all allowed. All possible values of energy are allowed. Now, one question, guys. if you see this, right? If you were to plot E versus K, what shape of that function do you foresee? Let's say you plot E versus K. How do you think the shape of that function is gonna be? You plot in an X and Y plane, you plot E versus K. How is that
It will
function?
have a quadratic fashion.
Yeah, it's a quadratic function. That's right. And how is a quadratic function? The shape. What's the shape?
It's a, I don't know how to say it in English. It's a parabola.
It looks
Yeah,
like a
it's a
U.
parabola. Parabola. It's a parabola in English.
Okay.
Okay, it's a parabola. That's perfect. Now, is it upwards or downwards?
Upwards. It's positive.
Upwards.
Perfect. That's E versus K. This is an energy continuum. No restrictions, no bands. We'll see this for the other case, and you'll see how this changes. But so in the case of a free electron, and this is what matters, right? This is why I get this equation. This is why this equation becomes so important. It's because when I'm plotting E versus K, and remember, this plot is going to be super relevant. E versus K, we'll have to learn to plot these two sort of numbers, E and K. When I'm having a free electron, when I'm having an energy continuum, the parabola doesn't have any stops, any interruptions. It's all a continuous parabola. No restrictions, E versus K. The parabola just continues on and on and on and on and on forever if I wish. And obviously, as Natalia said at some point, it's gotta be, or Fernanda, I don't remember, it's gotta be positive. Yes, because energy is positive, because K is gonna be, because the mass and the Planck's constant are always positive, and K might be negative, yes, but it's a square. So it is going to be positive at the end, right? The value of energy. Okay, is it clear so far, guys?
Yes, it's clear.
Okay. Another question, guys. Do you think K is a vector or a scalar? It means a quantity. Do you think K is a vector or a scalar?
It has to be a scalar. It's a wave number. I will think.
You will think. Okay. Does everyone agree with Fernando?
Yeah, I agree with Fernando. I feel it is color as well.
K is actually a vector, guys. And therefore alpha is a vector. And yes, you could say, well, it's the wave number. Yes, it is the wave number, but it's actually called, I mean, if we're gonna be very specific, it's actually the wave vector, okay? And I say wave number because usually we just take the scalar. So that means we just take the module of the vector. How do I know it is a vector? Sorry, let me now delete all these. K is related to P. What is P? P is the momentum, right? And if you remember, and I do have that equation at the beginning, I think, the momentum is related to the mass times the velocity. And what is velocity? Velocity, absolutely a vector, isn't it? So if I have the momentum equal to mass times velocity, velocity is a vector. This is a vector. And if k is related to the momentum, and momentum, if velocity is a vector, momentum is a vector. And if k is related to the vector, then definitely k is a vector. So when we're taking this, yes, we're just taking the module of that vector. So that means, you know, the scalar of that vector, just the module of the vector. But actually k, and you people usually call it the wave number, but it's actually the wave vector, okay? I just want to mention that because I want that concept to be clear, but at the end, trust me, what we will use is just the module of the vector. We'll just use the number. But k, so for you to understand it better, the k vector, the wave vector, describes the wave properties of an electron. Just as you know, one describes the classical mechanics, in classical mechanics, the particle property of an electron within the momentum. Well, that's basically the way the k vector describes the wave properties of an electron. And therefore, it needs to be a vector, right? So if you sort of, you know, want to be, I guess, want to understand even further, k becomes just proportional to the momentum, right? And, you know, momentum describes, in classical mechanics, describes the particle property of an electron, while the k vector, or the wave vector, describes the wave properties of an electron. Okay, just to clarify a bit of k, but at the end, again, the main concept here is what's happening with the energy. Okay, guys, can I jump into the next topic? Is everything clear now?
Yes, mister.
Okay, next case then. Now I don't have an electron in a potential, in a potential free space. Now I don't have a free electron or a free flying electron. Now I have what is called a bound electron. So an electron in a potential way. So it's bound to its atomic nucleus. So let's be simple, and it's not just me wanting to be simple, it's in general how people approach this to understand and sort of simulate what's happening. Let's assume that an electron can move freely, but now it's bound. So it's not allowed to move freely anymore, like, you know, infinitely freely and all around it, this space. Now it can move freely, yes, but between two infinitely high potential barriers. So now I have basically, let's say you before had an entire swimming pool for you, right? And you were able to move all around, you were able to swim all around the swimming pool. Now you have these lanes, you know, these sort of plastic lanes that divide the swimming pool, and then you have your lane, right? You know, lane 1, lane 2, whatever. And so now you're only allowed to move in your lane. You're not allowed to jump into the next lane. You're now restricted. So that's basically the case now. So now the electron can move freely all around this. It can move freely all around this, but only around this. Because now it has two barriers. That's why it's a bound electron. It has two barriers. They are, for simplicity, consider infinitely high potential barriers. But so I have two barriers now, two blocks now, that restrict the movement of the electrons only to that space within the barriers, within these blocks. So the electron is not allowed to escape from this potential well. It's not allowed to escape from this space. And therefore, the wave function will be 0. Sorry. If x is less or equal than 0, so that means if all this space, the wave function is 0 because I have no electrons there, or if I have x greater or equal than a, means this space, this is an a, right? Let me, yeah, it might not be clear, but this is an a, okay? This is an a, letter a. So, oops, well, doesn't matter. So here in this space, the wave function is also going to be 0 because I have no electron there. The electron now it's contained within this well. So the wave function will have a value in that range, but outside that range, outside that well, it will be 0 because I have no electron there. Is it clear what's happening now, guys? Okay, let's go again with the 1D case. Let's not consider the 3-dimensional case. So that means it's gonna move only in this direction, right? It will be able to move, sorry, in this direction, only in the x direction. It will not be able to move in y. This will not be allowed, and it will not be able to move in z, only in the x direction. Question, guys. Do you think the Schrodinger equation will change? So that means, do you think this equation, let me label this, will it be the same equation as this? Or actually, will it be the same equation as this? Will anything change in this new case? What do you think, guys?
Now we have the potential energy.
Now you have the potential energy. Okay. So you think now the Schrodinger equation will be exactly like this one, like the left one, right?
I mean, I think so.
You think so? Okay. Is everyone agreeing with Fernando, or does anyone disagree with Fernando?
I think that we are only changing the boundary conditions. We're giving more precise values. So the equation at the end will be the same, but the solution will have additional constants added to the ones that we got previously.
Perfect, Miguel. Yeah, the equation will not change. What changes is the boundary conditions. I didn't have boundary conditions before. There was nothing restricting the movement. Now, if we just think about, and I'm gonna explain this, Fernando, with this simple example, or I guess clarification rather than an example. Fernando, the electron, oh, come on, okay. The electron can still move freely within these barriers. There is no potential energy inside the wells. Where I have the barriers, where I have the potential energy, is here. It's just at the end. It's not that I have within the well potential barriers. I don't. The electron can move still freely inside the well. But again, inside the well. Therefore, the equation doesn't change. The equation is the same. So an electron in that well, in that region, it's written as before. It doesn't change. What changes definitely is the solution, as Miguel said. Because now I have two boundary conditions, right? And therefore I will have another constant for sure. And we'll do this in the tutorial, but now the solution is this one. So I have this additional component because why do you think, especially this, why do you think, and I'm not talking about the constant because obviously I will have another constant because of the boundary condition. But why do you think I have these guys? Negative I alpha x. Well, it's because before, for simplicity, I was assuming I don't have any, okay, so it doesn't matter. I'm just gonna do it here. Before I had this, the electron was moving freely, but what we were considering actually was just moving in the positive x direction. So it was moving freely. There was no any barrier to stop him, to stop it, but it was moving only in this direction. So it's like it's going all straight from Ambato to Guayaquil, no stops, and go straight and straight and straight. Here, there's a difference because now it's going to, let's say from Ambato to Guayaquil, but then the roadway is closed in Guaranda, let's say, and it has to come back. And therefore is now not only moving in the positive x direction, and remember we're considering the one-dimensional case, it will be the same we're considering the three-dimensional, it would just be positive y and positive z, but now, as you know, it comes and sort of encounters this well, this wall, so this block here, it has to come back. And therefore it's moving in both positive x and negative x direction. So it's coming back and forth, back and forth, back and forth permanently. And that's why you have this negative x direction here. Before you only had this positive x because we were assuming it was moving only in the positive x direction. Now that electron is coming back and forth, positive x and negative x direction. And obviously I have another constant that, you know, it comes from the boundary conditions I have. In alpha, Natalia, you asked for this. Alpha is the same, or has it changed? Alpha is the same value, has the same value. Okay, so this is the solution, right? Perfect, guys. Now, let's consider one boundary condition. Let's consider the boundary condition now. You see my screen, right? For some reason I lost it. Okay, now it should be clear. The one boundary condition it's going to be similar for that condition of a vibrating string. So that means it doesn't vibrate at the 2 points where it's clamped down. So guys, for how do I get this? It's the one boundary condition. How do I get that?
You evaluate the function as 0.
Okay, the function is equal to 0. Okay, and what else? When is the function equal to 0?
For x equal to
0,
0 and
A.
a.
Miguel, and
A.
x equal to a. The first case, the first boundary condition is going to be x equal to 0, right? Remember the diagram, the figure here. The function equal to 0 at x equals 0. So when x equal to 0, right, e to the 0 is 1, right? So it's basically 0 equal to a plus b. And therefore, b is equal to negative a. And that's what I got here. Did we all follow that, guys? First boundary condition applied. Did we all get that? Super clear, super easy, right? Okay, next boundary condition, yes, function, y function equal to 0 at x equal a. When x is equal to a, right, I have the wave function equal to 0. Remember that b is equal to negative a, right? So this basically becomes a times e to the I alpha a minus a times e negative I alpha a, right? I'm just replacing b with negative a. And therefore you can take, you can associate common terms. So a common term, and then you get e to the I times alpha times a minus e to the negative I alpha a. I think this is quite clear and easy. And from this to this step, did you guys learn about this famous equation? Oops, sorry. Did you guys learn about the Euler equation?
Yeah, we did.
Yes. Yes.
Yeah, okay. So if you use the Euler equation, you can get from this, let me just, if you use the Euler equation, you can get from this to this. I might send it that as a homework probably, or we might do it in the tutorial. I'll see. But basically, you get that, and that's, let's say, the solution, or with the other boundary condition. Okay. But now I can see something, right? Now I can realize that there is a restriction. I just put in a box the important part. What is the restriction, guys?
A is
Alpha
a
times
constant
A.
into 0. So the argument of region is a multiple of p. for the relationship is equal to 0.
Okay, of pi you mean, right?
Yes.
Okay. Okay. Yes, because for this to be accomplished, for this term to be 0, a is a constant, it's not going to be 0. I is the imaginary number, so this term is never going to be 0. This first term is never going to be 0. So I need this term to be 0, right?
Yes.
A is not going to be 0 because A is a value, but I need the product alpha A to be 0. And as Jose said, which is perfect, for that term to be 0, the sign of, sorry, not the product, the sign of the product alpha times A gotta be 0. And for that to be 0, well, it's gotta be pi, or well, it can be 0, sign of 0, or it can be an integer multiple of 0, right? So this is what we see now. So this is going to be valid only if the sign of alpha times A is equal to 0. That means if alpha times A is equal to n times p, n times pi, sorry. So that means n can be only and only 0, 1, 2, 3. Now, and here comes the key. Alpha is equal to what, guys? N times p times pi over A. And this is the new alpha. And therefore, if we go back to this equation that hasn't changed, right? This hasn't changed. The energy is equal to h squared divided by 2m times alpha squared. This hasn't changed. If we just now replace our alpha, well, it will be pi squared n squared over a squared, right? And we get this. That's the energy now. As long as n is equal to 1, 2, 3, n is not going to be 0 really, because the energy itself is not going to be 0, right? But it can take any integer value, right? Why I don't take n0? Because if n is 0, that means E will be 0, right? And if the energy is 0, I go to the equation and I know that if the energy is 0, then the function itself will be 0. And that's not valid, right? It's only valid at the boundaries or, you know, away from the boundaries. But I need now to consider the cases inside the well. So let's say just next to the wall, you know, that wall that has an infinite potential. So I'm not going to consider the case of n equals 0 because again this will lead to energy equals 0, and this will lead to the wave function equal to 0. Okay, the wave function equal to 0. But that's only the case in the boundaries, right? And now I care about the values of energy inside the well. So I care the values of energy about inside this well. No at this wall, no at this wall, no. I'm inside the Y. Therefore, the energy shouldn't be zero. The Y function is not zero there, right? Because obviously there wouldn't be electron wave, and that's not the case. Okay, so n is equal to 1, 2, 3, any integer value. So now what's happening, guys? We now see a difference from the free electron case. Because these little things that we change, these boundary conditions, now permits that only certain solutions of the Schrodinger equation exist. Basically means that there will be solutions only when n is an integer, right? And we all saw that n must be an integer. That means the energy now assumes only those values that are determined by n as an integer. All other energies are not allowed. Well, these allowed values of energy, it's what we call energy levels. So now I don't have that energy continuum as before, where all values of energy were allowed. Now I only have levels of energy that are allowed with n's as an integer. Is it clear, guys?
I have a question. What is C? Is a
Oh yeah, C just the constant here. C is just so it should be the Planck's constant square times pi squared divided by should be 2ma squared. So it's just the constant of this. Let me, so C in the graph, C is this. C in the graph is just C. It's called C in the graph, right? That's C. That's just, let's say, because all of these are constants, right? So you just group them all and you just call it C. It's nothing relevant. It's just C. Okay. And this E1 that you see here, this 1C, okay, it's called the 0-point energy. So if you realize, actually, the energy doesn't really start at 0. It starts just above 0 with what's called the 0-point energy. That in this case, it's 1C. That means when this is equal to 1, right? N equal to 1, and C, obviously, the value, whatever that is, right? So N equal to 1. That's called the 0-point energy, just a concept that might become helpful in the future, but nothing super relevant, okay? But the thing here, the message, and I'm gonna, with this, I'm gonna finish, guys. We've got an energy quantization. So there's only discrete, only certain possible values that the energy can take. And that is called an energy quantization. The lowest energy level I can get is the 0-point energy, which is the one right here, the 1C. So, and that's what I want to repeat, the lowest energy of the electron is not really at the bottom of the potential. So it's not really, if you remember the graph, something like that, it's not really here. It's not really here at the bottom of the potential. It's just above the potential, right? Just above, sorry, that limit. Just above that bottom when n is equal to 1. That is the 0-point energy. That is the lowest energy that the electron can take in this case. Is it clear, guys? Any questions?
The higher value of what's
Of the energy can be infinite. N can go, as long as it's an integer, it can be infinite. Yeah.
okay, thanks.
Yeah. This can go forever and forever, right? Forever and forever, and it just goes on and on. As long as N is an integer. But now it doesn't, it can't take any value, and that's what matters. Okay, guys, I have to say goodbye because I have another class. I'll see you on Wednesday. There is class on Wednesday. And that's it. Thank you, guys. Take care. Please, any questions, send me a message. I'm happy to answer any questions. And remember the paper to me, right? You can ask me questions all the time.
Just a quick question. The tutorials will be every 15 days, or would it be every week?
Probably every week. There might be 1 week that there will not be tutorial, but hopefully it will be every week. Yeah, I mean it depends on how we're progressing and the material we have to cover in the tutorial. So it will all depend on how we progress in during the week. But ideally, I'm gonna try to make it every week.
Perfect. Okay, thanks.
Okay, thanks, guys. Bye bye.
Thank you, Mr. Bye.
Thank you.
Bye.